So when we talk about different trophic levels, the amount of available energy in one trophic level is going to decrease by 90% to the next trophic level. And one of the main reasons for that is heat loss. About 60% of the available energy in one trophic level is going to be lost as heat to the environment. And therefore, there is a limited number of trophic levels in an ecosystem. And that's why they also get smaller and smaller and smaller as you go up. Now, if we look at the standards over here on the right, the two things that College Board is asking us to focus on is a change in energy resources such as sunlight and how that can affect the number and size of trophic levels, which is what we kind of saw with the different latitudes on planet Earth. But you can just totally picture if you cut off sunlight, then you don't have photosynthesis, then you don't have producers, then you don't have trophic levels above. Now, the second standard here, a change in the producer level, can affect the number and size of other trophic levels. Let's go ahead and look at a quick example. But before we look at that quick example, here's another way that we can show energy pyramids. They're not always in that triangle shape. They can also be represented by bars. But what you notice with the numbers here is that it's roughly only a 10% of one trophic level is what's available stored in the organisms, the biomass of the next trophic level. I really like this second quote on the side from Wikipedia. It says, a pyramid of energy represents how much energy initially from the sun is retained or stored in the form of new biomass at each trophic level in an ecosystem. I think that's a great way to describe it. Now, the next standard here, changes in energy availability can result in changes in population size. So we can think about if you have like an El Nino or a lot of rain in a particular year, then the plants are going to do very well. Like I live in Southern California where we don't get rain very often. So years where we have lots of rain, we have lots of like super blooms and lots of plants growing. Well, if you have lots of plants, then you can support lots of herbivores and then lots of consumers. And the trophic levels generally do well. On the opposite, if an area goes through drought and your plants die, then you're going to have the collapse of the trophic levels, which we can also see in different regions around the world. Now, one of my favorite examples of this is an unfortunate event in the Galapagos in the 1970s where they went 551 days without rain. So there was about a year and a half of drought. Now, during that time, the plants on the islands suffered, and the plants that produced small seeds withered up and died, leaving only plants that were kind of drought resistant that had large seeds available on the island for the birds to eat. And so this is an example commonly talked about in natural selection, but here we can see that the finches with the smaller beaks, because they didn't have any energy, there wasn't food for them, they starved to death. And what we saw was a change in the population size decrease by 80%. And that really came down to a lack of producers on the island. And therefore it couldn't support herbivores. And if there were large predators that ate the finches, then they wouldn't be supported, etc. And it would like ripple through the trophic levels. Now, this is, my next slide is just a quick continuation of my first video on metabolism. Now, this is not necessarily populations, but rather just individual organisms that kind of, if an individual has an excess of energy, they're going to store it, and it will lead to the growth of the organism, versus if there's a net loss of energy. So there's not enough food, and there's a loss of mass that could lead ultimately to the death of an organism. And so this here rounds out our discussion on energy flow through ecosystems. I'll probably make a few extra supplemental videos on like matter and reproductive strategies that all deal with energy, but maybe aren't directly mentioned in the standards. All right, great job.